And one of the major functions of the heart in general, just to pump blood, but the heart has two pumps. There's one on the left and one on the right. And in general, we say, oh, the left-hand side pumps the heart to the general circulation, while the right-hand side pumps the heart to the lungs. So the lungs typically is near the heart, so the right-hand side doesn't generate as much of a force. Can you guys see this? Kind of bad drawing in a way. And then, so you can always tell the difference between, the heart has four ventricles, right? So we call this is the left, this is the right atrium. This is the right ventricle, because this is all relative to the patient, right? Not you. This is the left atrium, and this is the left ventricle. And if you look at the wall of the heart, on the left-hand side, this side, it's going to be much thicker on the wall on the right-hand side. Okay. And one of the, and of course, there's this atrioventricular valves on the left-hand side, atrioventricular on the right-hand side, atrioventricular on the right-hand side. The left is thicker, yes, because it has to pump the blood that goes to the systemic circuits, whereas this one just needs to go to the lungs, right? So then the hydrostatic pressure on this side is 120 millimeter mercury over 80 millimeters of mercury. This is systolic and diastolic pressure. I'm sorry, it kind of doesn't work too well. And one of the laws that says pretty much the Frank-Stalling law of the heart. And there's several ways to look at the Frank-Stalling law of the heart. And people can say, okay, so the heart tends to be pumped harder when it's filled with blood, right? And it will pump blood feebly if it doesn't fill with the heart. So the amount of blood that comes back to the heart, we call it a venous return. So when the venous return is more, heart contraction is harder, if you will. And that's usually the other ways that people look at it is that, oh, the end-diastolic volume is high, the stroke volume will be higher. Okay, so that's, if you don't know what that means, I can explain to you a little bit later. But the idea here is that the heart pumps the blood. So in short, you can say this, that the amount of the amount of the blood that the heart receives is going to contract or eject that volumes of blood. Essentially, that's how you can think of. So let's say, if it's received 70 mLs of blood, it pumps out 70 mLs of blood. Okay? And it does this so that the right-hand side and the left-hand side pump the same volume equally. If it's not, then there's going to be a backup, a congestion, right? So that's why we say that. And here is that if there's a left side heart failure, which means that the venous return from the lungs, right, going to the left-hand side, it cannot go into the left-hand side because the left-hand side cannot pump. It receives the blood, but it cannot pump that out, right? It cannot pump that out. So then what happens to the next volumes of 70 ml or so? It stay back up in the lungs. So we call that the backward effect is that you're going to get a congestion in the lung. It's called pulmonary congestion. You can see that. As pulmonary congestions, that mean now the blood from the right-hand side cannot go to the lungs anymore. right? So that's also back up as well. So we call that peripheral resistance will be increased over there. And then ultimately, most of the time, you started out with the left-hand side heart failure, and the right-hand side heart failure is probably due to left-hand side heart failure. So typically, you start out with left-hand side heart failure first, and then you're going to have your right-hand side heart failure. And when the right-hand side heart failure is in, the right-hand side you see, let's say, 70 mLs of blood, and it's not pumping that 70 ml out, so that the next 7 that comes in, it cannot. So it's right. So it's going back all the ways that, so then you can get this whole systemic congestion, if you will. Okay? And it could lead to edema everywhere. You know, we call that anosarca, for example. And yeah, so yeah, that's like edema everywhere. Okay. And of course, now that if you have a left-hand side heart failure, the oxygenated bloods in the lung go into the left lung. The lung. Okay. Okay, yeah. Okay, that's another way too. Sometimes it's very small for me to see. I don't know how to make that text better, bigger. And where was I? Oh yeah. So if the oxygenated blood's in the lung, coming back to the heart, to the left-hand side, and the left-hand side has to pump that blood out. But because the left-hand side, right, is filled, it cannot not receive any more blood. You're going to get congestion. So that's the backward effect. The forward effect is that there's no blood, that oxygenated blood that leaves the left-hand side, right? So that means that there's no arterial blood at all, right? And that means that there's no oxygenated blood, right? So, you know, the volumes, we call this cardiac output. Cardiac output is defined as, of course, you should know, cardiac output is equal to heart rate times stroke volume. No. It usually is the left-hand side heart failure first that leads to pulmonary edema. If you have pulmonary edema, most likely you have pulmonary edema first, then you're going to have the right-hand side heart failure. Okay, but in this case, it's left-hand side heart failure first that leads to pulmonary edema. Okay. So that's that. Where are you typing? I can't see. Oh, can you type in the chat? Okay. I have to switch back and forth. Okay, so cardiac output is heart rate times stroke volume. Okay, that's cardiac output. And that's what you see here. That's what this thing is. So that's what this thing is, cardiac output. So because the stroke volume is defined as the amount of blood that leaves the heart per contraction. So if we say cardiac output is heart rate times stroke volume, if there's no stroke volume, cardiac output will be decreased. If cardiac output is decreased, that means your tissue will not get enough oxygen, right? So in other words, cardiac output decrease, blood pressure will decrease, and I'll tell you that your blood pressure, I don't like to switch back and forth, but I think I wrote this to you already. Blood pressure is determined by 5 factors. Right? which is one is heart rate, 2 stroke volume, which is the same as cardiac output. 3 is blood volume. 4 is peripheral resistance. And 5 is viscosity. Okay. So any of those, when the left-hand side heart failure, you will see low cardiac output, low blood pressure, less blood flows to the kidney, of course, renal. You're going to have the kidney attempts to bring up your blood pressure, and the kidney regulates that in several ways. There's a short-term way. Short-term way is to release renin. What is renin? What does renin do? Renin is the enzyme that converts angiotensinogen into angiotensin 1, of course. The kidney can also does it, regulate it in the long-term way by secreting this thing called EPO, erythropoietin. And EPO is erythropoietin, which is the hormone that stimulates the hematopoietic stem cell into more red blood cells development. Okay, so of course, red blood cells get oxygen. The more oxygen that under anemia, hypoxia, you want to make more red blood cells so that you can keep up with the demand of the organ need. Right? And this is very true that if you go up in a mountain, the oxygen is very low. You're going to put out more EPO. The idea there is to make more red blood cells to help you acclimate it to a higher altitude, for example. So interestingly, so it's the cell in the kidney that is sensing how much oxygen you need. If your red blood cell is low, I mean, low oxygen, you need to put it more. And how do you do that? The kidney put out EPO. Okay? That's how it regulates it. The kidney also play a role in regulating sodium too, right? Because the attempt here is that if your blood pressure is low, it's going to under response of we're going to see it later on, it's called the adrenal cortex put out aldosterone. Okay, so the adrenal cortex will secrete aldosterone. Okay, so aldosterone then will stimulate the kidney. Aldosterone will yes, when blood pressure is low, you want it to bring it up, and the aldosterone will stimulate the kidney to take back sodium. Right? So why are you going to do that? Well, it takes back sodium, water will follow, and trying to increase your blood volume. This is all the mechanism of trying to increase your blood pressure. So you stick with the fact that blood pressure is regulated by those 5 things. Okay? Blood volume, blood viscosity, peripheral resistance, right? Cardiac output, heart rate times stroke volume, which is the same thing as cardiac output. Peripheral resistance, yeah, okay, number 4 that I have up there. And so if your blood pressure is low, then that's what it's trying to do. It's trying to bring in your pressure by regulating sodium from the kidney, and also an attempt to make activated the renin-angiotensin system, which is, by the way, the innovative of the renin-angiotensin is angiotensin 2, right? And angiotensin 2 does 2 major things. Angiotensin Two, one thing it does is that it's a major vasoconstrictor. Vasoconstrictor. Okay. Constrictor. And two is that stimulate the adrenal cortex to secrete aldosterone. And now you know, okay, see, now aldosterone stimulate the kidney to take back sodium, and then to increases the reuptakes of water. Basically, sodium go osmosis. It's just less water come out as a part of the fluid, and then you have your attempt to bring up your blood volume. So your blood volume here will increase, and then increases a little in that. Okay, that's an attempt in trying to see what happened. So in general, we say, okay, if you have a left side heart failure, what is the forward effect? The forward effect is that the blood pressure is dropped. What is the backward effect? The backward effect is that you're going to have congestions in the lungs. Okay. Any question with that? It's a concentrated, I mean, it's a lot of saliva. I kind of introduced to you as part of the function of the heart in there as well. Okay. So the question is, when do you give diuretics? Okay. So the other thing, right? We saw that blood volume play an important role in blood pressure. So someone who has hypertension, whose blood pressure is very high, right? So one way that you can bring the blood pressure down is to attempt to bring down the blood volume. So one way you bring down the blood volume is that you give diuretics so that people can go to the bathroom, for example, right? So then decrease your blood volume. That's how you can help someone like that. Someone who has edema, which is like swelling, there are apparatus that can sort of like help squeeze, and particularly someone who is bedridden. You can basically massage the leg and have the fluid flow in the venous circulation, but you can also try to give diuretics so that they can avoid it. So then that fluid will leave the body, if you will. Okay. Shamika, you have a question?
You said when you give the diuretics, they attempt to bring down the blood volume. Is that because their blood pressure is high?
Yep. So the question one of your colleagues asked, when do you give diuretics? And I'm telling you that if blood pressure is high, give diuretics. Okay. Yep, that's right. All right. The electrolytes, is very important. Sodium and potassium are the two major ones. Typically, intracellularly, you see high levels of potassium. Extracellularly, you have high sodium. I would say that this is the yin and the yang, and you need to know these numbers in the plasma as well. What is the concentration of this in the blood, for example? And usually in the sodium is very high, it's like 142 milliequivalent per deciliter, whereas potassium is more like 4. But potassium is very high inside a cell. And whenever you have a condition that leads to high levels of potassium, so we call that hyperkalemia, and because the potassium level inside a cell is very high, so whenever you have a destruction of the cell, right, potassium can come out. So your potassium level could be higher, right? So we call that hyperkalemia. So hyperkalemia is too much. I'm just going to write K for potassium. could be due to cell destruction. And this is very true too. Is like if you give someone wrong blood, it's called mismatched reaction. If someone whose blood type is A and they receive B blood, for example, that could lead to destructions of their red blood cell. And of course, if you have too much potassium, hyperkalemia over a long time could lead to cardiac arrest. And that's what they usually do if you kill somebody in Texas and they give you, it's capital punishment. They give you potassium, bolus injections of potassium. And too much potassium, it just interfere with the repolarizations of the heart. So then your heart will stop beating. Calcium and phosphate, of course, both of them is very important in formations of bone, but they actually, in bone, they form calcium hydroxyapatite, which is basically a component of calcium and phosphate together. Calcium and phosphate tend to bind together and precipitate our solution, so you really don't want these two to be together. In skeletal muscle, the way that, intracellularly, you have high levels of potassium inside a cell, okay? Because inside the cell you have high levels of phosphate, and that's because cells are hydrolyzing ATP, right? So ATP gives rise to hydrolysis of ATP to ADP and phosphate, which is basically adenosine triphosphate to adenosine diphosphate and inorganic phosphate. That's usually ATP is the energy unit. We need it to do it in any kind of active transport and movement, for example. You hydrolyze it all the time. Some enzyme might use ATP to phosphorylate protein as part of intracellular signaling. So phosphate is very high intracellularly. And certainly you don't want calcium to be around with phosphate because they're going to form calcium phosphate. So what the skeletal muscle does is that it tends to put calcium into an organelle known as sarcoplasmic reticulum. Right? You compartmentalize it to prevent it from binding to phosphate, for example. But you need calcium for a number of things. Skeletal muscle contraction needs calcium. Calcium is needed for blood coagulation. Calcium level also regulate in terms of the strength of contraction. If you have too much calcium, your heart is going to contract very harder, if you will, as opposed to low calcium. And certainly one of the other ways that I told you that you can also regulate is this regulate by sodium potassium channel. Is what? You mean potassium or calcium? So the question is this regulated by sodium potassium channel? And my question is, what is this? What is this? Samika, you have a question?
Sorry,
Samika?
I accidentally clicked it.
Oh, okay. Okay. Yeah, so too much calcium can make the heart contract harder, right? So when the heart contracts harder, there will be more blood ejected from the heart, right? So we call that stroke volume increase. Right. So in other words, if you go, every time it goes like this, let's say hypothetically, it ejected 70, well, that's very high, but it's ejected 70 mLs of blood, 70 mLs of blood, 70 mLs of blood, 70 mLs of blood, right? So when it goes like this, so now you get 80 or 90, 80 or 90, right? It contracted harder, so that means more volume of blood leaves. So stroke volume increase, blood pressure increase, right? So how can you decrease this heart contraction? You can give them calcium channel blockers. Calcium channel blocker will cause the heart to contract weaker, so that stroke volume will decrease. Okay, does that make sense? So certainly calcium play an important role. Magnesium, okay, so magnesium play an important role in typically as a cofactor for DNA polymerase. Right? Some enzymes need magnesium to work. Without magnesium, it doesn't work. Some other enzyme might use manganese, but some kind of metal that is needed there. And of course, wherever potassium is, chloride will follow. So it is sodium outside in the plasma is about 142, roughly about 130 or something is chloride. So we go back here to look at the slides, share with you. This is a good one you need to know. So the plasma level, I told you mentioned already. Sodium plasma level is 142 milliequivalent, right, per liter, and the potassium is 4, and you can see here chloride is about 100. So these are 3 good numbers to know. If you want, also I want you to know intracellularly potassium level is 160. You can see very high. Sodium is 10, very low relative to outside, and then again chloride is 2. So this just kind of have like a general idea what is the normal number. So maybe in an exam I might give you an abnormal number. If you can recognize, here's a sodium, it's this level, here's a potassium, it's this level. So you see if you can think and say, oh, normally potassium is only 4, but potassium now is 8, right, or 10. So that means, oh, there's something's wrong there. Could be lysis of the cells or something like that. So you got an idea. All right, so we talked a little bit already about acid and base balance. Can someone give me an example of a respiratory acidosis? Carolina, are you there?
Yep, that's the one that I didn't get to do. But is it edema? I put hypoventilation. I don't know if that counts though.
Yeah, that's essentially the same thing. I mean that if you're not normally breathing as your normal rate, which could be like 15 breaths. So by hypo, I mean you mean below in ventilation.
Mm-hmm.
Yeah, I think that's count. Oh yeah, asthma, COPD. Yeah, that's all should be right. Yeah, and in fact, we kind of says right here too. An example of metabolic acidosis. And again, I think some of you might get this right, so then I'll probably will write 2 exam questions regarding the acid and base here. And good number to know is physiological pH is 7.35 to 7.45, and the number that is below that 7.1, and you can conclude that's acidosis. Right? What causes it? Is this guy is under have no insulin, for example? Well, then he is diabetic, for example. If you produce a lot of ketone body, that is metabolic acidosis. As you can see here's acidosis, metabolic acidosis right here, diabetic ketone. kidney failures, for example. And that would be under anaerobic respiration, of course, that's like lactic acid production. The acid is acidity. So good example of those are metabolic, good example. Respiratory, COPDs, good example of metabolic alkalosis is typical of someone who here alkalosis ingests too much base, for example, antacid. Good example of someone who has respiratory alkalosis is at the opposite of hypoventilation. Someone who blow out too much hyperventilation, for example. Hyperventilation, blow out too much CO2, for example. Alrighty. This is an interesting slide, and trying to shows you what happened inside the cells. And let me see if I can do this. Okay, good. This is a good equation to know. Okay, so water plus CO2 will give rise to this. I'm going to see if I can write this down. Oh, I can't write it. Okay, yeah, maybe. Okay, so it's actually is this H2CO3. That's carbonic acid that breaks it down to hydrogen ion and bicarbonate. And the reaction is reversible, okay? And because if you have too much hydrogen ion, it combines with the bicarbonate, which is part of the plasma, and it shifts the reaction here, so then you get a lot of CO2 that can be blown out. And likewise, if you have too much CO2 in the hypoventilation, for example, your CO2 will increase, that will react with water, give you too high hydrogen ion. You can see that, okay? But the most important, that inside the red blood cell, there's an enzyme called carbonic anhydrase. Okay. And this enzyme, carbonic anhydrase, catalyzes this reaction really fast. Okay. And this is inside the red blood cell. And this reaction that occurs all the time, in the context is what we call it. Let me go and grab that here. In this context, what we call it internal respiration. Internal respiration. Respiration. And external respiration. And what this means is that internal respiration is defined as respiration is defined as gases exchange between the internal respiration is between the blood and the tissue. Okay. So internal respiration is gases exchange between the blood and the tissue. And this is really meaning is that the blood, right, loses oxygen and gain carbon dioxide. Or you can say that in the internal respiration, carbon dioxide loading. Okay, anyone has problem with that? Any question with that? So in the internal respirations, gases exchange between the blood and the tissue. So you get the oxygen the blood loses the oxygen, it dump off the oxygen, right? And at the same time, it gains the CO2, right? Because what happened, the cells in the tissue use up the oxygen as part of cellular respiration. It degrades this carbon glucose to CO2. So in the tissue, CO2 is very high. So CO2 is loaded into the blood. So that's what we mean that internal respiration. Okay, so external respiration is the gases exchange between the blood and the lung. Right? And so here's the opposite. The opposite is that CO2, I'm going to write this, CO2, that's mean carbon dioxide, unloading, I mean it's going to come off the blood into the lung, while oxygen is loading into the blood. Does that make sense? Anyone have a question with that? Okay, good. So let me go back then to this slide. So one of the other important things is that I hope that you're going to learn later on, and is when we talk about the respiratory system, this is known as the Bohr effect. Okay? The Bohr effect. Okay. So the Bohr effect I hate to go back and forth between the text and the figures because every time it changes the figures, it's just, there's a lot of movement. So the Bohr effect essentially is that it's saying that so external, you get more oxygen. Okay, cool. Wait, what's the, where am I? Someone just writes something I couldn't see. If you have a question, can you raise your hand? Okay, all right, I'm going to go on then. Okay, so here, as you can see, this it doesn't go too well. It shows you here is that, what does this say? Fixed acid, amino acid, ketone acid, okay, gets into the plasma, for example. But in here, what you see is that what happened is that you're going to see this reaction that has occurred here. Right. This is the exact question that I told you earlier with CO2, and CO2 expels out in the lung, and then hydrogen ions. Right. If you have too much hydrogen ion, it will basically shift this reaction this way, and this is so the Bohr effect is told you is that under acidic condition, the oxygen, the level of oxygen that comes off of hemooxygen is very high. Okay, and so if you can imagine inside the cells, right, in terms of the external, in terms of internal respiration, right, you're going to have more CO2 into the blood, right? CO2 is in the blood. CO2 is in the blood will shift the reaction, will go this way, and you can see that you have high hydrogen ion. And so what you see here is that there's going to be a chloride shift. And a chloride shift means that the bicarbonate now goes into the blood. The bicarbonate goes in the blood, the chloride will goes out as part of the internal respiration. And the bicarbonate goes in with the hydrogen ions can shift the reaction so that you can get, All right, forget about the Bohr effect, what you can see. In the, let me start over. In the external respiration, okay, so external respiration is, think of it as gas exchange between the lungs and the blood. And where the oxygen level is very high, okay, so oxygen will go in here, will get oxygenated, for example. Then that means that the deoxyhemoglobin will move out the hydrogen ions. And the hydrogen ions then could basically leave, right? So then you can get this, the reaction is shifted, right? Like this again. Oh, hydrogen, actually that's supposed to be bicarbonate that give out to hydrogen ion plus this bicarbonate. So these reactions occur really fast in the blood, and what happened is that because the other equation that you wanted to know is probably something like this. This is hemoglobin, okay? And typically, if the hemoglobin doesn't have any oxygen, we call it HHB for deoxyhemoglobin. And if you add it with oxygen, right, it will give rise to this, which is HbO2. HbO2 is oxygenated, and it gives out the hydrogen ion. You see that? And so what this really means is that in the blood, in the lung, because the oxygen is very high, this oxygen can bind to hemoglobin and it kick out this hydrogen ion. You see, that hydrogen ion. And this hydrogen ion is very critical because this hydrogen ion might be needed to bind to the bicarbonate, which is part of the blood that goes into the blood. And then it shifts the reaction, then CO2 can expel it out. Right? That's the external respiration. It's rather complicated, but I understand that. And the opposite of it is true, is that in the internal respiration, what happened is that CO2 is very high. This is actually CO2. CO2 is going to go into the tissue, go react with water, and it shifts this reaction, right? And you got this hydrogen ion. And what Bohr's effect is that whenever you have this right here, this is oxygenated hemoglobin with hydrogen ions like this way, is going to kick this out. Right? Whenever you have high hydrogen ion, it's going to kick out the oxygen, so the oxygen can leave the blood, and then the hemoglobin now has become deoxyhemoglobin. And I don't know how much of this that you need to know, because it seems like it's very, very extensive. The most important thing that I want you to know is that the bicarbonate that you see in the blood contribute to the release of CO2 from the blood. Okay, so it's actually, the bicarbonate goes in and out of the red blood cell. Okay, depends on whether the red blood cell is play a role in the internal respiration or external respiration. That's the idea. And one of the ways that the kidney can regulate your the pH in the body, because the kidney is the only system in your body that can get rid of hydrogen ion directly. Okay? Whereas in the respiratory system can compensate for, if you have acidosis, it can compensate it by reducing your hydrogen ion, but it does it indirectly through this system. Okay? It couples that hydrogen ion with the bicarbonate and it pushes this way. Okay, so this system is important in get rid of hydrogen ion by the respiratory system, whereas this hydrogen ion here, free ion, can be get rid by the urinary system directly. Okay, that's the key. And the bottom line is the bicarbonate play an important role in the internal respiration and external respiration. Maybe I'll come back to that next time when we study the respiratory system. Okay. All right. So why don't we stop here and we'll take a little break. And I'm going to stop the recording. This way, it's good to have different segments of the recording. And then I'll come back with 5 minutes. Does anybody have a question?